Given an array of string, find all the shortest unique prefixes to represent each word in a given array. What is the shortest unique prefix? It just means when you are iterating through a single string, what is the minimum character that you can reach to distinguish yourself from the rest? For example, the word zebra. When I'm iterating through the word, when I reach Z is enough to distinguish this word from the rest, because there's no other word with the same prefix, being Z. So for zebra, I return Z. For the word dog, the word D alone is not enough, because duck and dove also start with D. So you continue, D-O, is D-O enough? No, because dove also starts with D-O. They have the same prefix. You have to have D-O-G to distinguish yourself, aka unique prefix. So in this case, you have to return the whole thing, which is D-O-G. For duck, D-U is enough. For dove, you will return D-O-V. Now we will tweak these questions a little bit. We will make two modifications to the question. The first is the output must be in the same order as the original input. So Z should return at first, then we return dog, then we return DU, then we return DOV. The return order should be consistent with the input order. The second modification is we will assume that some word is a prefix of another. For example, if we add another word that is do, D-O, then D-O will be a prefix of dog and dove. For the word D-O, we will just return D-O. So this is the test case we're going to use. The input is an array of strings, so this is an array of string of 6 elements. Our output is also an array of strings. It's supposed to return in the same order. Dogs, we will return dog, because DOG is the minimum prefix in order to distinguish itself from the rest. Then for does, we will return do. Then for do, although DO is a common prefix because they also have DO, but since DO is already the end, so we will just return it. F is the unique prefix. This one is just APPL, APPS. We're going to use the try data structure. It is highly recommended that you watch the video by Tushar Roy beforehand. However, our try data structure will be slightly different from Tushar Roy's try data structure. Tushar Roy's try data structure will have content of a Boolean variable that is called end, as well as an array that is maybe, let's name it children. The length can be 128. So that is the try data structure that a normal try will have. However, in our use case, we're not going to have a Boolean variable. We're going to have an integer variable. Let's call it count. So how do we solve this question? There are two phases. The first phase is to build the try. So let us now build the try. The try starts off with the top level node with the content of count, which is initialized to 0, and an array that we can call it children. The length of the array is 128. We choose 128 is because we do not know whether the input is going to have capital letters or small case letters. How are we going to build the try? We're going to iterate over each string inside the input array. So the first element inside the input array is dogs. And we're going to iterate through each character inside this dogs string. And we will start from D. But before we do that, let us check out the ASCII table. The lowercase a is 97. So you can tell from the integer number 97 all the way to character Z is 122. These are useful to us. And if you care about capital letters, it will be 65 all the way to 90. So you can see lowercase d is mapping to 100. And we go back here. our lowercase d, so there's a 100 somewhere here. The ASCII representation is the character D. Now let us talk about what this array children really is storing. It is storing 128 null pointers, right? That means it is not pointing to anything. And now I am checking the character D or querying the position 100. Because it is pointing to null, we need to create a node. We need to create a node and point to the new node. This new node is initialized with the count of 0, but we are going to increment it by 1. So now its count is going to be 1, and it also has a children array which is size 128. Conceptually speaking, what does this 1 mean? And what does this 100 or D mean? And how does the data structure of try relate to these two concepts? Well, I hope that you can see from our root, which is this node, we can access one of our child nodes by the index 100 or character D. So that means in our try, there is the prefix of D. And as of right now, because the count is 1, there's only one word that starts with the prefix of D. Let's continue. Now we have iterated to the character of O. So this is the current node. There's a O somewhere here. I'm just going to say O. Because O is currently pointing to a null node, we have to create that node. It is initialized with a count of 0, but we will increment by 1. Of course, it also has a children array. So this is the current node. So we know in our try, we have the prefix of DO and once, all right? So let's keep going. We arrive at the character of G. So there's a G somewhere here. This guy is G. Because G is currently pointing to null, we need to create a node, and this new node is having the count of 0, but we increment it. So this is the current node. This means our try has the prefix of DOG. Let's continue. We are at the character of S. So there's an S somewhere here. Because it is currently pointing to null, we will need to create it and point to the new node. The new node is initialized with the count of 0 and a child array. So we know we have a prefix called DOGS, and this prefix exists once. Because we finished iterating over the docstring, for this node right here, this node, all of its 128 array elements are null pointer. Let's keep going. We finished dogs, let us do does. So let us do does. The first character is D. We come back to the root, all right? We come back to the root and we ask the children array, is your character D or integer index 100 pointing to anything? Oh, it is. Previously, it was pointing to null. That's why we have to create it. But now it is pointing to something. It is pointing to this guy. So what we're going to do is to increment the count of that guy to 2. What this means is our current try has the prefix of D twice, or there are 2 input words with the prefix of D. Now, what is the significance of that? If in our input array, there is only one string with the prefix of D, for example, DA, and all the other words is like G, F, A, X, blah, blah, blah. Right now, we are assuming that guy is 1. Because there is only one occurrence of prefix D, then for this string, the shortest unique prefix is just D. Now, let us assume prefix D has 2 occurrences. What that would mean is somewhere down the line, there's another string, it's called maybe DB. Then D can no longer be the shortest unique prefix, right? Because there's another one with D. In that case, you have to keep going, maybe DA, and you check, is the count at DA 1? If it is more than 1, you have to keep going. So the significance of this count is that this guy is a count. If this guy is 1, I can be sure that whatever string that from the top level root to my current node, that string is the shortest unique prefix. However, if this node count is 2, I have to keep going. Let us continue. Now the current character is O. So is O pointing to anything? Yes, it is pointing to this guy. So our pointer will move to here. This is the current node. We will increment the count to 2. The significance is DO cannot be the shortest prefix, of course, unless your whole word is DO. So we know for dogs, you cannot choose DO. For does, you cannot choose DO. Well, for do, it's fine. So for dogs, you have to keep going, maybe DOG. For does, you have to keep going, maybe do. And it ends up being the case. Let's keep going. Now the current character is E. Does E exist? No. Maybe this is E. E is currently pointing to nothing. Because you're not pointing to anything, we need to create it, right? So we create a null node, increment the count, come with a child array. Then our curve will move on to here. The significance is do occurs once. Then we move on to character S. Somewhere here there's a S. Is S pointing to anything? No. So you have to create it. Create 0, increment to 1. The child array significance is does occur once. Our current pointer will point to here. So we finished does. Let us move on to do. The first character of do is D. Then we ask the current node, this is the current node, is your character D pointing to anything? Which is equivalent to saying, is your index 100 pointing to anything? Well, yes, it is pointing to this node. So you increment the count by 1. It will be 3 now. So it means there are currently 3 words with prefix D. Then we keep going. The current character will be O. Is O pointing to something? Yes. O is pointing to this guy. So we need to increment the count to 3. The significance is there are currently 3 words with the prefix of DO. Then we continue. Oh, we have finished. By right, DO should not be the minimum prefix because the current count is not 1, but DO is the whole word, so we will just return the whole word. Now let us do the word fish. F-I-S-H, the current character is F, so there's a F somewhere here. And F is pointing to nothing, so we need to create it. Create, this is F, this is 1, the child array. Then you have I, then you go, then you have S, then you point to another thing, you have an H. You get the point. I will not go through all the steps. I have cleaned up the try. So our try has been finished building. Now let us move on to the second phase, which is to find out the actual shortest unique prefix part. I've already touched upon this phase previously, but I'll just very briefly walk through how to find out the shortest unique prefix for dogs and do. Let us walk through dogs. I'll keep track of a current string. It is initialized to null string, and this is the current pointer, which is at root. Let us iterate over the string dogs. The first character is D, so we add D immediately to the current string first. So current string is D. Then we ask the node that D is pointing, which is this node, is your count more than 1? Well, the count is 3, is more than 1, so we need to keep going. So current move to here. Then our current character is O. We add O to current string immediately. Then we check, is the node that O is pointing, which is this node, is the count more than 1? Yes, it is more than 1, so you need to keep going. So current pointer here. Then we move on to character G. We add G immediately to the current string and ask, is the node that G is pointing, which is this node, is it more than 1? Well, it is 1. It is not more than 1, so we break out of the loop, and the current string is dog. Let us walk through do. The current string is initialized to null string, and the current node is the top level node. So the first character is D. I add D immediately to the current string and ask, is the node that D is pointing, which is this node, is it more than 1? Yes, it is more than 1, so you need to keep going. Current. So now the current character is O. You add O to the current string and ask the node that O is pointing, which is this node, are you more than 1? Yes, you are more than 1, so you go there and you keep going. There's no more character left, so we return do. Let us move on to the actual coding. This is the array of strings. I have dogs, does, do, apple, and other strings. And I'm going to create a class called try and call a public method called unique prefix. I'm going to pass this string v inside, and this function is going to return me back the result. So I may as well just initiate a vector of string called result, return result. Vector means array, by the way, and return it to res, and I will print it. As of right now, because I return back a empty array, it will print nothing. In this class, we are going to make use of this try node data structure. So the actual data structure of the try is this try node. It has two data. The first piece of data is the count, which is an integer, is initialized to 0. The second piece of data is the array that I initialized to size of 128. It is pointer to an array, and this is the initializer list. All the elements inside the array inside the children array will be null pointer. So let us work on this method. We're going to have two phases, and the first phase is build try. Let's pass the words in, and we're going to do private, have a method called build try, and take in the array of strings. Let's call it words. It's going to be void. Let's initialize the try node data structure. Let's call it root. And in my try constructor, let us initialize the try node. Now this is a heap allocated pointer, so we need to have a destructor in order to free the memory. Let us write a clear method. So clear is going to take in the heap allocated pointer. Oh, I need to pass in root. So I need to loop through all the children. So if the children is pointing to something, I need to clear the children. And delete. In order to build try, we have to iterate over the input array of strings. So word is the single string. Let us put some new line. and let us iterate over each character of the word. For each word, I will need to create a new pointer that references the top level root, and it will say, well, does the current character exist? Does the current character exist? Well, if it does not exist, I need to create it, right? I need to create a equals new try node. Well, let me just put some bracket. Then I will become my children. Then I will increment the count. Just to do a sanity check, I'm gonna write a print function that print out the try to make sure that it actually makes sense. So I'm gonna pass in the root, try node root for in I equals 0 plus 128 plus I if root children I out char I white space root children I count. Then I will recursively print it. Let's run it. So let's see if this makes sense. A is 3, okay. A is 3, P is also 3, okay. Then this P is 1 because of apple. Then L is 1, E is 1, okay. Then we R because R is here, apricot. C is here, O is here, T is here, D is 3, okay. Looks like it makes sense. Okay, so let's keep going. We have successfully built the try. We don't need this print anymore. Let us go back to here. After we finish the try, we need to loop through the words array again. Words. Have a new pointer for the root and have a current string that is initialized to null. Then we do something, rest dot in place back, which is basically push cur. So what we're supposed to do here, we are supposed to iterate over the word and check. Oh, we are supposed to immediately push the character. Then we check, is the node that you are pointing have the count of 1 or not. So the node you are pointing is this. Do you have the count of 1? If you are 1, we are gonna break. All right. If you are not, we'll keep going. So let's run it. Oh, I need to go inside the children. Dog, do, app, API, f, APR. Let's just add in null string. Make sure it doesn't break. Okay, null string is working. Fishes. If I sh, looks like it works.